it's a great pleasure to introduce and to have Keenan Weirobeck give this last talk of our workshop. Keenan is the co-founder and head of product and engineering at Zipline. Zipline, as you can kind of see right behind Keenan, is it's a drone delivery service, and it's the world's first drone delivery service. So it has, and I think Keenan's going to talk about the amazing work that they've done in Africa in delivery of medications. I've been watching how they've been developing their products delivery service in the US as well in other countries. Keenan is what can I say? Stanford alum, worked for a while at Ross, the PR2 development, and has just built this beautiful company, Zipline. And take it away, Keenan.
Cool. Well, thanks for having me. It's great to get to speak with all of you. Yeah, so this is kind of a fun talk. I kind of made it to be a little bit behind the scenes, these are the kind of talks I like to go watch, which is if you're seeing like kind of what are the nuts and bolts, what does it take to make something really work? And by the way, I know I've got about a half hour here. This is only about 20 minutes of content, so I'll keep an eye on the chat window if you want to ask questions. This is a relatively small group, so we can keep it interactive if well, folks want to. I don't know, Claire, if that's okay, but excellent.
Yeah, that's great.
All right, well, I'll just dive right in. So a little orientation to Zipline. So Zipline started in Rwanda about 3 years ago. This is Rwanda. We now have 2 distribution centers operating there. You can see the service radius of a distribution center as those larger circles. So that's 80-kilometer radius. And we'll talk a little bit more of the nuts and bolts that it takes to actually sort of serve that kind of radius day in and day out. And then you can see all the hospitals and clinics that we're currently scaling up to serve there. Last year, we started operations in Ghana. Ghana is a much bigger country, and we currently have 4 distribution centers up and running there. Well, that operation is doing incredibly well and scaling beyond our imagination this quickly. And then earlier this year, we started our first operation here in the States, a distribution center in North Carolina that's been doing well, COVID response. It wasn't the original purpose of the partnership with Novant Health, the health system out there working with, but COVID happened. And so we pivoted to work with them on that. And hopefully after that, we'll get back to what we want to do with them, which is basically being the physical side or the delivery side of their big push to home healthcare. Yeah, so that's a little bit of a taste of where we are. Just to kind of preface some of the stuff I'm going to show you, especially when we get into the autonomy bits at the end, we have a lot of scale coming. We have a partnership we've announced with Walmart, basically delivering their health and wellness stuff, pharmacy kind of things outside from distribution centers. We'll be launching with them in Arkansas next year. And then we have a whole bunch of other customers here in the US and other countries around the world that we're gearing up to serve. And so a lot of what my job is and what we work on at Zipline is basically how to scale and scale responsibly and do it in a way that is both a great customer experience for the doctors and patients we serve, as well as responsible from a autonomy, safety, and airspace integration points of view. So, okay, all right. So just to kind of bring this to like super concrete numbers to kind of paint a picture of a busy day at Zipline. This is actually a few weeks back now, so 425 flights, that's how many flights we did that day across our distribution centers and operations. We flew a total of 49,000 kilometers expressed in all the units that you might be interested in, including my favorite. That's 1.23 times the circumference of the Earth in one day. Distance per flight that day was 116 kilometers. Average longest flight was 188 kilometers. That's as the flight goes. I mentioned, we'll talk a little about that in a second. Average speed that day was 106 kilometers per hour. So anyway, just kind of bring it down to, we talk at Zipline about sort of big aggregate numbers, how many millions of miles we've flown in total, but I kind of like to zoom in, kind of understand what does it actually kind of look like up close. So behind the scenes at Zipline, we got to start with reliability. So reliability is the cornerstone of our customer promise to the doctors. It's the reliability of our relationships with the regulators. It's the foundation of our relationships with our regulators. And it's, of course, the foundation of our relationships with the communities we serve, right? We're flying over people all day, every day, all conditions, at night. And it's very important that they trust us. When you're in the air, reliability is how you stay in the air. So let's talk a little bit about that. So in terms of numbers, there's one really key reliability metric we track, and that's how often do our zips land by their emergency parachute landing system. So they have an emergency parachute landing system basically for two classes of things. We can generally handle all single faults, but in certain multi-fault cases, we have to land by parachute. We can't keep flying, or extreme weather events that we can't get through. That's what the parachute's for. And so right now, it depends how you do the math, but we're right around 1 in 5,000 flights result in a parachute landing. And that's kind of a fuzzy number. There's a fun hard number to share. 8,874. That's our biggest streak to date. That's the maximum number of flights between two parachute landings in actual operations, and that equates to a little over 1 million kilometers, just for reference. And this is a big deal. If you haven't had the pleasure of working on something that's operationally fault tolerant, it's a world of complexity and engineering that's quite fun and very challenging, and much harder than I thought it would be to really achieve in a practical way. And so let's talk a little about weather. So weather is one of the biggest challenges when it comes to our parachute landing rate. It's just one of the biggest challenges in general. It's the biggest thing that can literally knock us out of the sky. And so let's get into a little bit about how we deal with weather. So everybody can still hear me, right? When I get talking into quiet. Okay, I see Claire. Okay, perfect.
Yeah, we can hear you really well, or at least I can.
Excellent. It's like presenting to silence. Well, let's talk a little about weather. So if you haven't been near the equator where we do most of our operations today, I like to show this video. Let me play in a second. And okay, just to kind of give a number here, in operations today, right around 1% of deliveries are delayed by weather. So it doesn't mean it doesn't happen. There are some weather conditions where we don't fly. And there are some conditions where the planes will automatically, we call it mission abort, where they'll basically turn around and fly home. And in aggregate, that adds up to right around 1% of our flights are delayed by weather. But generally, we do fly in like all weather conditions. That's an actual photo of a zip about to go into a thunderhead, which is a pretty challenging environment. Move off that video. That was louder than I thought it would be. I hopefully you got a sense of that video. Rain rates near the equator, not like up here north of the equator. We regularly see rain rates, easily, 75 millimeters per hour rain rates, sort of 3+ inches per hour, like more water falling in the rain than in a typical shower in the California, like a bathroom shower in California. So there's all kinds of things we do to actually enable flying in this kind of weather. We do a lot of testing. Some of that testing looks like this. This is one of our systems that we affectionately refer to as a craptastic wind tunnel. So what you're seeing here is off to the left, it's a blower, just a big old industrial blower and a garden hose sprayer. And we're just blasting that plane with 130 kilometers per hour driving rain. What's nice about that test is it's very easy to run. It's obviously a very low cost test to build, and it helps us understand, our wet weight. It helps us make sure that does water drive through seals? We don't think it should, and so on. Anyways, it's a really nice, very, very simple way to test, and a way that we can very easily regression test. We also build up more sophisticated test rigs. This is a video of one I'm about to play here. For those of you who aren't familiar with a whiffle tree, this is the very classic way of testing an aircraft wing in aerospace engineering is a whiffle tree. It's basically a series of levers, mobile style, right? A series of levers sized so the point load gets distributed across a wing the same way a load would get distributed in flight. The only modification here is this one's dynamic. So it's not usually in the aerospace this is done statically to failure, and here we do it dynamically to really understand fatigue life and well, as you'll see here, we can really beat up on the planes. And not only do we know, do the wings not fatigue off, which is obviously important, but do the battery latches hold, right? The battery is half the weight of our vehicle. It's 10 kilos just right there. And so anyway, this is a shipping container converted to environmental chamber, built out with this thing we call the Pogo cycler that you're seeing here, where we can cycle humidity and UV and temperature and everything. So anyway, that's another example of the kind of testing we do for weather. Are you hearing sound from the videos? Is that you are? Okay. You can hear me over the sound recently?
Yeah.
Excellent.
Yeah, we can.
Okay. I love playing the video clips, but I never know what's actually happening. Okay. So so what you're seeing here are 3 different videos. So this is another shipping container converted to environmental chamber. This is a cold one. Get good temperature swings. And here this is an example of testing, not the drone side, the zip side as we call it, but this is testing the ground systems. So this is if you haven't seen How We Land, you should check that out. But if you have, we basically pluck these aircraft out of the sky, basically with a line between these poles you're seeing. And on the left, you're seeing testing at very cold, minus 20 degrees C at full speed. And get that to play again. There it goes. In the middle, you can't see much at all because we can actually recreate snow conditions in this chamber, which is a lot of fun. And then on the right, you're seeing the high temperature testing. And this is, we want to make sure that these systems, they hold up in the real world. So in this testing program, this kind of ground testing includes both the aircraft and the ground system side. In order to pass, it's about a 1,500-day testing program. Okay, now to be clear, that's not all in series. That's not all serially done. We parallelize as much of that as we can. But to pass all the tests, it takes about 1,500 days of testing, of test time. And as you can imagine, you don't generally pass the test the first time you try to pass them, especially when they're this abusive. So, but this is absolutely fantastic. It enables us to very fast. We have a dedicated team that just builds these test systems and runs them, and enables us to flush out all of these issues, on the ground. One second. Okay, so there's a little taste of sort of the testing ground reliability program that's involved in really enabling us to fly in all weather. This is getting into more the flight software side of things. So what I'm going to show you here is a replay of flight logs from a flight going through one of those thunderheads. So to be clear, this is not a simulation. This is a visualization of flight logs. And just the orientation of that before I play it here. Hold on a sec. Okay. So the blue line, the vertical blue line there, my finger was lost. That's the route the plane is trying to fly, along with the target zip location you can see as a silhouette there at the top. And then you see the actual zip location that we call our drones zips, with 2 little vectors. One is the forward velocity, and the other is the wind. And those are both ground forward velocity and ground relative wind. And so, let's play this so you can get a sense of what's happening here. So we're on track, right? Crabbed over, that's normal with a crosswind, but we're on track. But as you can see, the winds have just picked up a lot and we've lost almost all of our ground velocity. And so here you can see we're getting way off course. Now, keep in mind, we're only seeing let me pause it for a second, but you're only seeing the sort of the lateral error. This is also developing a lot of error in Z, altitude error. And so here we are, 91 kilometer per hour wind speed, -6 kilometer per hour forward ground velocity. And this is what it looks like for that plane to fight its way back on course and to regain its ground speed. Developing a system that robustly does this, handles the energy of the aircraft incredibly efficiently, and can do this in the real world, right, where you have all kinds of constraints, right? Usually these kinds of really rough situations are over mountains and you don't have unlimited space around you to deal with it and accumulate error. So anyway, there we are, back on track. There's still a huge crosswind. It's died down a little bit, but we've now gained back 56 kilometers of forward velocity. So we're actually making progress again to our destination. Okay. So that's a little bit about weather. Let me pivot from that to range margin. This is another one of those kind of unsexy behind the scenes numbers that just really matters a lot to make this thing work. Now, as you can imagine, so I mentioned our 80-kilometer service radius. So that's out, and of course we have to fly back, so 160 kilometers round trip. And we designed the system to have, well, a lot more range than that, so we can do these deliveries, all day, every day, all weather. And so that we effectively designed for this target of 285 kilometers, plus even then some margin. It's a little complicated to get into, but let's get into some of the factors that all feed this. So weather, of course, is one of them, but there are other things we need to carry margin for. So one of those is really nicely shown on this image. So this, and it's really simply put, you can't fly straight. As much as you think you can in a drone, in the real world, you don't get to, for lots of reasons, and I'll get into a few of them. So this is an image of what we call the sky map, basically our routes, our highways in the sky around one of our distribution centers in Ghana, right outside of the capital, Accra, you're seeing there. And so all of the white lines and the red line, those are the routes. And all of the orange dots, those are delivery sites that we are serving today. And then right in the middle, that Z, that's our distribution center. And so there's a lot of things that we are not flying over, right? There's keep outs that the government doesn't want us to fly over for many different types of reasons. We have a database basically of population density that we used as basically an optimization layer in our planning. We have databases of things like where are every school in the country, and we don't fly over any schools, for example. And these are all knobs we turn to optimize for safety. And then of course, there's also terrain and mountains, and we'll talk about that in the next slide in a second. Before I move on to the next little video clip, let's talk about for a second about that red line, because it's kind of fun. So that big circle you see, that's the normal keep out around the international airport in Accra. So as you can see, most of our routes don't go in there. At the beginning of the COVID response, the government of Ghana came to us and asked if we could help with sample delivery. Their military only has a few helicopters, and they didn't want them just to be reserved for COVID sample transport. And they have, since the beginning, they've had very good and very aggressive test turnaround targets. And so what's been happening since the beginning of COVID is COVID samples have been getting delivered to that Z, and we've been shuttling them up to like 5 or 6 flights a day. Basically, once we have a box full, directly to the backyard of one of 2 testing labs in the whole country, which is at the end of that red route you see going right into downtown Accra. And as you can imagine, it was a pretty involved conversation with both the regulator in Ghana, the airspace regulator in Ghana, and the organization called ICAO. They harmonize all the airspaces internationally, basically to work out the airspace integration plan for that route to do that. But it's been huge. It shaved a solid day off the test turnaround time, which in Ghana, their goal is 1 day turnaround time. So a day is helpful, is very important to hit that goal. Anyway, so we've done, I think we just hit 6,000 or 7,000 samples, which, by the way, sounds like a small number until you realize how well Ghana's managed the outbreak. And then it's actually a fairly large number because their contact tracing is quite strong, and their overall rates have been managed very, very well. Anyway, so that's that red route going into downtown Accra. Moving on. So I was talking about range margin, all the things that basically add up to the margin we need to carry. This is a nice animation that shows one of our routes in Rwanda. And let's check it out. So basically, Rwanda is very mountainous. You're seeing the outbound route and the inbound route, basically path that we take to get to these delivery sites. Off to the right there, that's a fork going off to another delivery site. Notice how we're flying, sort of through mountain passes. We have to follow all these regulatory rules about hugging the ground. We have, again, all those things I mentioned around that are involved in the optimization. Of course, we have to make this close on what our plane can do, and in terms of its climb performance and descent performance and so on. Well, as you can get a sense there, this route, we're climbing thousands of feet in both directions, because the delivery site's actually at the same altitude as the distribution center. So you fly over these mountain ranges to deliver and fly over them on the way back. Anyway, that's another big contributor to the range margin that we carry to make this practically work. So we can't fly there direct. We got to climb the mountains, wind and weather. And then there's this whole other category of contributors to that margin that are really important. And I'll just give one example of that, for instance, an example, if you will, of the other category. Are the control surfaces on the vehicle are fault tolerant. So we have basically 4 on the wing and 4 on that V-tail. And if we can handle any failure, we've tested this crazy hard over failures, oscillating failures, whatever kind of failure happens in a control surface, we can keep flying. But of course, when that happens, the plane will have a mission failure, it will fly home. And now, it can have a lot of drag on the way home if that's a hard over failure, and you have to deal with that drag. And of course, all the other control surfaces are now fighting the effects of that hard over failure, adding more drag, and you still got to get home. Anyway, so that's another example of what goes into that other bucket that leads to this very significant sort of range that we designed for. And a lot of people ask, why fixed wing versus other things? Doing that range margin with anything other than a fixed wing aircraft for this kind of range would be a much bigger aircraft, and the economics of this just would not close. We looked hard at that, doing like some kind of VTOL. So anyway, just anticipating a question that may come in. So behind the scenes at Zipline certainly would not be complete without a tour of what we build. So part of the fun of this is kind of the unglamorous stuff, right? It's like what you're seeing here is the modularity of the aircraft, right? Make field service easy is so important, right? We have aircraft that have been in operations for years now. It's not because they're perfect or flawless, it's because they're easy to maintain. And then what you're seeing here is all the various pieces of the puzzle, all the automated testing required to test all those modules. And of course, not just the aircraft, we make the chargers and the batteries and the launcher, recovery system, and on and on. So let me pivot from there, talk a little bit about autonomy here. So I want to, to kind of frame our work in autonomy, it really comes back to our mission, right? So we have a mission to provide every human on Earth with on-demand access to vital medical supplies. Now, I mentioned a busy day from a little while back being, 425 flights. And that is a drop in the bucket of achieving this mission globally. And so while we're very excited about the progress we made, we are just getting started and hope to make all the progress we made to date look irrelevant very soon. And a lot of that comes down to autonomy and scalable approaches to autonomy. So let me talk about a couple of the areas that we're working in there. So we think of autonomy as sort of two buckets. One we call airspace autonomy, and the second we call perception-based autonomy. So I'm starting with the first bucket, airspace autonomy. And so what you're seeing here behind me, this is at one of our test sites in Kieran, California. You're seeing what we call one of the corner cases that we worry about. So the corner case that you're seeing here is what would happen if you had a bunch of zips up in the air, in this case, 16 of them, and they all came back at the same time. Maybe you sent a command or random chance. They all come back at the same time, and your recovery system, your system for landing these zips, is not working, like it's disabled. And so this can happen, right? Our recovery system has modules just like the aircraft, and if one of them has a fault, it can take up to about 20 minutes to swap that module out. And so you could have a queue of aircraft in the air, which is what you're seeing in this video. So this is 16 of our drones all queuing and waiting to land. And that is fully autonomous. And so is the follow-on behavior. So when you enable that recovery system, once it's ready to go, the zip with the lowest battery will land in the best health, and followed by the next, and that's completely automatic autonomous behavior. And since this is a nice and geeky crowd, that is a distributed behavior, and that is a fault tolerant behavior, and that's just very important so there's no master in the system like orchestrating that, and that is, of course, fault tolerance and reliability only matters insofar as it's a useful tool for our operators, right? And when things are going wrong, like a recovery system fault, the last thing you want the operators doing is trying to basically command things and figure out what's not controlling the zips. You want them to focus on their safety, getting the problem fixed, and you want the zips to take care of themselves while that's happening. So there's one little taste of what we call airspace autonomy. And there's a whole lot that goes into how to manage a ton of zips in the air at once. We're up to about 20 flying out of one distribution center at a time, and we're working our way towards hundreds over the next year or two. And so the other big bucket around autonomy is perception-based autonomy. And so this is what it sounds like. This is onboard sensing on the aircraft, detecting things in its surroundings and making decisions on board the aircraft. And I will stress that like we push all of this stuff on the aircraft. We only briefly consider things like trying to offload data to process it somewhere else or have humans in the loop to validate. Relying on communications in anything that we would consider safety critical is just something we have learned the hard way you do not do in this kind of operations. And by the way, even the US military, who's advised us, they're the biggest operator of drones in the world, the biggest reason they lose drones is because of loss of communications. So anyway, so we design first principle is like, don't rely on communications for the system to work nominally. So what you're seeing here is a picture of the first thing that we've been developing, which is detecting other aircraft. This is actually a photo during a live test where that zip is detecting and avoiding that helicopter. This is a really exciting capability for us. And it's we just submitted it to the FAA, which I'm very excited about, and we just got our first response, which is like, anyway, there's the first time Zipline has submitted a perception-based capability to a regulator. So it's kind of a big milestone for us at the company. It was quite an endeavor to get that confidence, to get that submission in. And then hopefully we'll have something fun to announce in a matter of months if they agree with our assessment that it's ready for operations. So yeah, there's a little taste of what we do there. I can't quite talk about the details quite yet because we're still getting those last patents out around how we do this, because it's pretty it's not what you would expect, I guess, from a sensing and point of view. Yeah, so there's a little taste of Zipline behind the scenes. This was a pleasure, and I look forward to answering questions in the panel.
Thank you, Keenan. That's a wonderful talk. Every time I've seen you give a talk, it's been a different talk, and it hasn't been such a big span. So it's just a sense of all the exciting things you're doing fit into a variety of different talks. So it's just wonderful.
Fantastic.
We have some time for some questions now.
Oh, okay.
If you'd like to ask a question, you can chat it, or you can unmute yourself and ask a question, whatever you prefer. Can I, while we're waiting, can I ask, just, I know you can't talk about this perception-based autonomy. So is it that the vehicle is recognizing the other aircraft in the vicinity?
Exactly. Okay. Exactly. Using onboard sensors. So it was quite a challenge to get that one figured out. And then even I think part of the fun of all this is, this is all very new for the regulators, right? This capability that the regulator refers to as sense and avoid or detect and avoid is something that's been talked about for a really long time, but like a Western regulator has never approved its operation, which is, to be clear, that some people think that's like impossible. It's not. The FAA is always approving new things, but it's a big lift for them to get their head around it, to really basically evaluate the risk, and really basically have that confidence that it'll work from an integration point of view in the airspace, have confidence that it'll work technically, have confidence that it'll work, day in and day out in operations. And they look at it from all those points of view. And so it's been fun putting together that argument that we have it figured out.
So there's another question Derek Knowles asks, related to this question we were just asking, because you constantly have many zips flying at one time along similar routes, what framework do you have for the zips to safely avoid each other? Is it strictly perception-based and doesn't rely on communication? Oh,
great question. No, so those behaviors are actually strictly communication-based and don't rely on perception. So those behaviors, so our aircrafts have multiple layers of communications radios on them. And those behaviors use two of them. There's a line of sight radio system, all the zips have, that enable direct peer-to-peer communication. And so basically the information required for that deconfliction is sent in that radio packet, sort of like a transponder chirp a little bit. And then it's also sent over the cell networks. So basically just sort of in parallel, the same information. And then of course, like, if the line of sight, which is the faster one, isn't working, and hopefully it gets through with the cell. And then of course the behaviors are designed so that, like, with basically degraded performance in mind. So even if we lose both communication channels, like the sort of defaults that planes will do based on the information they have, which a lot of times is like, I don't hear anybody, they will do things that are intended to optimize for safety, and basically using the sort of the vertical and lateral space we have to fly to kind of, well, optimize for minimizing the chances that they don't hit each other, even if they can't talk to each other.
But you said when you showed them circling around the test center in California, that was decentralized. So are the vehicles deciding based on some kind of identification number, which altitude they're going to fly at relative to the others? Is there kind of that basically, they communicate, and then there's some kind of
so they will. So they're all. So that they're in a giant hold. Think of it as just a simple circle, right? And they are doing two things. They are maintaining, basically lateral. Well, actually, three things. They're maintaining what we call nose to tail separation, right? So basically, they're spacing out along that circle, and that's a distributed behavior. They're also biasing themselves out and in, as well as up and down. And so they kind of are similar, sort of how you described it. They're basically kind of picking and kind of claiming, if you will, those areas. And then based on when the next plane shows up, it kind of hears what's there. And then we'll kind of decide the safest place for it to enter and kind of take its space. And then I shouldn't say when it enters, as the next aircraft enters, not only will the other aircraft create space for that next aircraft inside nose to tail spacing, but that other plane, it has sort of its own, it's got its layered behaviors, right? So if it's coming in and doesn't see space, maybe it doesn't know why, then maybe the planes don't hear it, or maybe there's no room or something. It has a layered behavior where it can actually turn around and go to what we call backup holds that are not ideal, but basically like it won't just like shove itself into the queue if there's no room.
Right.
So, yeah.
Okay, that's fabulous. Thank you. Any last question for Keenan before we have a short break before the panel? And Keenan, are you able to join us for our panel?
Yes, I'm very much looking forward to it. I may not be able to stay for the last half hour, but I'm very much looking forward to the first 45 minutes.
Great, which it's going to start in, Gare, 10 minutes, right? 12:45 Pacific. Yeah.
Perfect.
Any other questions? George, did you have a question?
Well, there is the one in the chat. Maybe we should go with that.
Okay. David McPherson asks, for See and Avoid, are you considering the new ACAS X standard at all?
We are. It's not something we use in our initial submission. The challenge with that standard is we haven't found it to be that useful when you're hugging the ground. And this is something that we've spent a lot of time on. But basically, when you're delivering, for example, right, you're very often you're in a valley, right? And you're hugging the ground and you're an aircraft. So you have limited, your turn radius is relatively, we're an aircraft, your turn radius is relatively limited. And so it's, we have not found a lot of value. Like we didn't find enough value in using that off the shelf for our initial submission. Just because of how practically limited basically our space is to work with. And then also part of the trick of this is like think about zooming out to the level of a regulator or one of our pilots in command overseeing all these zips, right? It's very important that the behaviors are very predictable and deterministic in the eyes of the people watching, overseeing the operation. And so how to thread that needle between essentially like how those routes I showed you worked and how they're designed and how they have built-in capabilities for things like holds and turnarounds and stuff like that. And what the regulators want to approve relative to those routes versus these kind of behaviors that, of course, you're kind of deviating. But of course, like it's not an arbitrary deviation. And it gets into really, well, in some cases, frustrating conversations about, hey, if we could turn to the right, we'd have a much better safety case. But they're like, no. The right, you're crossing this airspace boundary to a new type of airspace. You're not allowed to turn to the right here on this route. You can only turn to the left. And of course, below you, you're hugging a valley wall, so you really can't go down. And sort of figuring out the right way to make that work in conjunction, of course, with the performance of the sensors, right? So the sensor performance is tricky, right? So we have sensors. We, of course, also listen to transponders. And as we've learned, even transponder signals near the ground, they're spotty. ADS-B, people may have heard of this sort of new well, it's the newest mandated transponder that's semi-mandated. It's a very old radio technology. And it's, you know, something like 10% of the aircraft we hear are sending out garbage on that transponder. This is in our national airspace. So it's when you actually add all that in, we ended up doing something basically different. We studied it carefully and borrowed some of what we think are the best ideas in there to make it work.
Yeah. Great. Thank you, Keenan. That was a great talk. We're going to take, let's see, a 7-minute break now and return at 45 minutes after the hour for our panel discussion. Okay.
Wonderful.
Great. Thank you, Keenan, and thank you, Katie, and to all of our speakers this morning.